All right, so there's an F5 posted, but really the F5 is about to also tackle the first slide for today. So people at home have your slides in front of you, and I've twisted up that first slide of this lecture a little bit, but you'll be able to keep up on the whiteboard. Actually, they're reversed. So let's take a look. Problem number 1 should have made you think of pre-AP. Problem number 2 should have made you think of easy stuff from Monday. So we're tiptoeing in, but these are both strongs. That's the point. Look here for a moment. If you're asked for concentrations or pH of a strong species, it's the easiest kind that there can be, all right? Because you just have to find the negative log or use KW to help you out. You don't have to do any extra stuff. Both of these are strong because one of them is potassium hydroxide. That's a hydroxide bonded to a group 1 element. Strong. The other one flat out gives you hydroxide or hydronium, which is the same thing as H plus for all of RAP purposes. But that's the strong part of the species. So these are both the easiest types of examples, which is why I'm knocking them out quickly, because it's the weak samples that are going to require some annoying extra steps. But let's solve real quick. The first one, it's talking about KOH. All right, again, strong. So I'll just need to find the negative log of the concentration. The concentration that it gives me is 0.710. However, I know that the negative log of a base like this is going to give me a POH, which is not what the problem wants. Now, when you run the negative log here, we'll go negative log of 0.710. I get 0.149 molar. All right? There's my 3 sig figs. I'm sorry. All right, there's my 3 sig figs in my POH. But we want a pH. And I know that POH plus pH equals 14. So finding the value is easy. What's the answer? 13.851. We okay on the first one? Now, the second one is still strong because it's referring directly to hydronium and hydroxide. But here, and this one I did alter quite a bit from the slides, but it's using the same value. It gives you 0.450 as a molarity of H3O plus. All right? So if that's true, I taught you a special trick that connects H3O to OH, and it was KW equals hydronium, or just the hydrogen. All right, again, H3O plus and H plus are going to be one and the same for us. All right, times the hydroxide. What we know is that KW is equal to 1.0 E negative 14. So if you put this value into this spot, this value into this spot, solving for him is algebraically simple. It's ultimately dividing. The 1E negative 14 is a constant value for KW that we went over on Monday. It's a number that always exists. So 1E negative 14 divided by 0.450, I'm going to end up with 2.22 E negative 14 molar as my OH concentration. No, because this is a molarity, not a pH. 3 sig figs, 3 sig figs. Remember, constant values never dictate sig figs. All right, therefore the value of KW does not dictate anything. All right, it's going to be that value only. This is review so far. How are we feeling? All right, so definitely switch over to your spiral if you haven't already. All right, you'll want to zoom a little bit using the knob up top. There you go. Yeah, that's it. Don't break your stuff. And then we'll show that first slide real quick. It'll just reiterate what I just said. But anyhow, it says strong samples are the easiest, mostly because the reason that just works so directly is there's no equilibrium. There's no K value to dictate any math because a strong sample dissociates at 100%. Therefore, it's just the normal yielded error. But once you identify something as weak, suddenly there's a K value associated with it because it will dissociate at equilibrium, and now everything gets a bit more complicated. So, what are we going to do about weaks? First off, you absolutely have to be able to recognize weaks and strongs. One of the things on Schoology that'll happen is you'll get so into the longer process of analyzing weak samples that you'll run into a strong one that's sprinkled in there, and you'll work on it for 10 minutes and then be like, oh, what? And then you're all angry at yourself. All right? So make sure you identify the sample, all right, using the rules that you've already mastered. When you do analyze one as being weak, though, it's a Rice table that's going to be used. It's equilibrium, so it should make sense to you that Rice is making a comeback. By the way, I had a conversation with a professor at UTSA over the weekend. That's a buddy of mine. He's got his PhD in chemistry, and I mentioned Rice table in the middle of the conversation. He said, wait, what? I was like, a Rice table. He said, what's a Rice table? I was like, for equilibrium. He's like, those are ice tables. I was like, no, Rice. He's like, what's the R? I was like, for the reaction. And he's like, the reaction's already there. It's just ice. And I'm like, you're stupid. Like, I didn't say that, but I feel like I won the argument. Third period disagrees with me and says that he's a PhD, so he has to be smarter than me. But I'm looking for people to join my side. We're going to keep calling them a Rice table. Anyway, in the Rice table, it'll be Bronsted-Lowry, which we remastered on Monday, so you're good at that. And then we'll just be running the same type stuff. Really, I feel like today is not very challenging because we have all of these skills that are floating around in your brain. I just need to bring them together for your ability to analyze a weak sample. So, let's jump into a problem. Well, first off, guys, the bottom of these are giving you a step-by-step of solving. I'm going to pay zero attention to that during lecture. The reason I'm doing that on some of the upcoming lectures is because I know that when this stuff's mixed with other concepts, you get a little confused. So I'm trying to make the slides very useful to you because it gives you kind of a step-by-step protocol. But really, you need to be able to do it without looking, which is why I want you to focus on the problem and me, not on those words at the bottom. Hey, look at benzoic acid. Is benzoic acid weak or strong?
Weak.
How do you know it's weak?
Carbon.
Contains carbon. Man, you're sharp and I love you. Hey, let's analyze him with some rice then. Because ice would be stupid. Here's the deal. If it's weak, you automatically add it to water. If it's weak, you automatically add it to water. So I'm going to go HC7H5 O2, and we're going to add that to water. Equilibrium arrow and Bronsted-Lowry. Hey, is the water here going to act acidic or basic? It's amphoteric. It could be either. He's going to act basic because he has an acid being added to him. All right? Stop it. I'm going to steal it from you. No, put it somewhere different. Thank you. So we know that Bronsted-Lowry states that acids want to get rid of a proton, so we're going to get rid of that front H. It's going to make him C7, I have to write a little bit smaller, H5O2 minus. All right? And he'll be giving his hydrogen to the water, so he will become hydronium. Worked out? All right, so let's do the rest of our rice analysis. First off, the water is liquid water. He is never going to matter in one of these tables. We are given an initial concentration. All right, so our I is going to be 0.1 molar. All right, and we've created this solution by adding it. So initially, we don't have any of this product, which means we don't have to worry about any Q values coming into play here. The shift will be obvious. We know that I plus C equals E. So let's reflect that. And as usual, we're given a little extra bit of info so that we can move forward with our table. In this case, it gives me a pH. It says pH equals 2.59. All right. Hey, what can I get from that number that would be helpful in the rice table? I can get the concentration of the hydronium. And if I find the concentration of the hydronium, I would have all of the X's, and life would be so wonderful. If you remember, in order to do that, if you're given the pH, if you take 10 to the power of the negative pH, it will give you a concentration of H3O or H plus, whatever. So I'm going to go 10 to the power of negative 2.59.
Why is it specifically the hydrogen?
Because that's the entire pH system was based off the fact that water can give off hydronium and or hydroxide in predictable amounts.
Wait, so if this was hydroxide,
Then there would be more steps. Our next problem will do that. All right. So anyways, I get 2.6 E negative 3 as my concentration. And that will be of H3O. Yep.
Why did you use the other equation that we used before, the KW equals concentration,
Well, the KW requires me to know either the OH concentration or the H3O concentration. I don't know either of them. All right? So, hey, what did I find then? Well, look, if that's the H3O plus, I have found every single X that's in the problem, and now we're good to go. This wants the equilibrium constant. It wants us to find K. Now, if you remember, water has its own little special K, not the cereal, it's not breakfast time, but it's got its own little special K of KW for water. So acidic equilibrium is Ka, basic equilibrium is Kb, and those are very commonly used all throughout the AP exam, so make sure you know what all of your different Ks refer to. So now, let's go for it, all right? I can start with an unsubstituted equation because you're sharp and you would do that. That Ka is going to equal C7H5O2 minus times the concentration of H3O plus over the concentration of HC7H5O2. All right, so we made some graders happy there. Now we can sub in the values that we found, and we know that Ka equals, well look, these two numbers, these two top numbers are the same number, right? They're both this value. So I'm just going to write it as 2.6 E negative 3 squared. You don't have to do that. You can write it twice. The graders don't care. It's the exact same thing. All right. Over, careful on the bottom, it's 0.1 minus 2.6 E negative 3. It's important that you enter this as a singular function on your calculator, all right? Don't find one, find the other, and run sig figs a bunch of times. I say that because on the AP exam, all of their sig figs are under the assumption that you're running this as a singular equation, all right? So type it all in before you hit enter.
What type of calculator do you get on the APs?
Yeah, you're allowed to bring your own scientific graphic calculator. There is a list of restrictions, but I doubt that they hit anything that y'all carry. Do you get 6.9 E negative 5?
Yes.
What are the units of K? Nothing. Questions before I erase?
Yes, how did you get the
I mean, it's this number squared divided by the difference of those.
On their own area.
Okay. All right, you can move to the next one. Now, this next problem just has one extra little thing to it. But that's my job, is to prepare you for extra little things. So let's start off by the word ammonia. Somebody yell out 2 things you know about ammonia the moment you hear it. Okay, that would be, okay, so 3 things. The formula is NH3. It's weak and it's basic, all right? So make sure that you definitely know that. Ammonia is a weak base, always. So let's eat rice. Ha. I did that on purpose, guys. So ammonia is NH3, as we just said. Since it's weak, we automatically add it to water with some equilibrium stuff. It's a base. Bases are protons acceptors, so ammonia is going to become ammonium. And water gave away a proton to make that happen. Our liquid water here is not a part of the fun. And now we can start to look at the information in the problem. We have a starting initial concentration of, again, 0.1 molar. Not real fun, but whatever. It's just the number. Get all of our shifts ready. I plus C is E. What information was a little extra this time? Now, that looks like the exact same info that was extra last time, but who can find the difference in this problem?
They have to subtract by 14 to get the POH, right?
Ammonia is in acid.
Don't you need to get the POH?
You'll have a lot of ideas. In the last problem, it gave us pH, but in our problem, we had hydronium, so there was a direct connection. But this time, there's not. I can't just find this X as directly as I did last time. All right? So what's the easy solution, though? Instead of using pH, let's use POH.
I literally said that.
Now, some of you are pointing out that there's another way to skin the cat, and you're absolutely right. All right? But we don't have time to investigate all ways. As long as it's chemically correct and you show your work, then life is good. But this looks like it's going to be 2.87. Now, this is the value that we would want to use in order to get an OH, of course. So therefore, if we go 10 to the negative 2.87, I'm going to get 1.3 E negative 3 as my molarity for OH minus. Are you with me? And guess what that means?
What?
I found X. All right. So we'll do an unsubstituted friend here. We know that my Kb is going to be the NH4 plus times the OH minus over NH3. If we sub it in, we know that my Kb is going to be 1.3 E negative 3, and ultimately it's squared, multiplying by itself. Over 0.1 minus that value. Anybody want to share their KB?
1.71 E negative.
Yeah, I think it's just 1.7 though. 1.7 E negative 5. Yeah, I've got 2 sig figs divided by a max of 3 on bottom, so 2 sig figs will win. Want to see the most annoying type of problem to end class? Yeah, you do. Welcome. Can I erase? You say no just to say no? All right, show us the last one, Vanna. The moment that a Ka or Kb is given to you, just like in our last unit over general equilibrium, it's usually a bad sign mathematically for you if they already give you one of the Ks. Because that's what led us to quadratics. Now, if we take a look here, CH3NH2, you wouldn't identify it as an acid because it doesn't start with H, right? When you're given one of those funkier compounds, if you can find nitrogen in him, that's your indicator that it is a nitrogenous base. Kind of works the way ammonia works, even though you just have him memorized. All right, but it was mentioned briefly on a Monday slide. All right, nitrogenous bases are always weak. Therefore, we must add him to water. So let's get ricey. CH3NH2. CH3NH2 being added to aqua at equilibrium. It's been identified as a weak base. So it will receive a proton, turning them into CH3, NH3 plus. And water got rid of a proton. Taking a look at our initial concentration of 0.712, we'll set up the rest of our rice table.
Wait, so is this problem kind of working backwards?
I mean, so far everything's been the exact same, but yeah, now we just have the other side of the equilibrium equation, but this one is less friendly to solve for. Now, there are some words in here that you've got to really watch, because while I don't doubt your ability to do the math, especially after last unit, you want to make sure that you understand what the answer you're getting is. So make sure that you really follow your variables and what's what, so that you don't do everything right but then answer the question wrong just because you misanalyzed your own work. Now, the extra information it gave us this time is a KB, all right? It says that the KB is equal to 4.4 E negative 4. All right? So the KB will be referring to hydroxide because it is the equilibrium for a base. All right, so we can prepare our unsubstituted equation by saying that KB is going to equal the CH3 NH3 plus times the OH minus, the hydroxide, and that'll be over the CH3 and H2 concentration. Of course, we don't have the values to solve for X as directly as we did last time. So as we sub this in, up top, my KB is 4.4 E negative 4 equals, all right, I like to put that over 1 for ease on my brain, and that'll be X squared over 0.712 minus X.
Why? Oh.
Compare my unsubstituted to my substituted. It should show you why. Remember, we take everything from the E row and put it into the equation. Questions up to that point? All right. So as we begin to cross multiply, we'll find that X squared is going to equal, we have a distribution to do here. So I'm going to go 4.4 E negative 4 times 0.712 at the beginning of my distribution. And I'll end up with 3 points. Hey, keep in mind, real quick, this is important. I don't think I said this. That KB is a constant value, all right? The K values that are established for different acids and bases are constant values. And as we've learned before, constant values don't have bearing on sig figs. Therefore, I will get 3 sig figs from this distribution. So I'm going to get 3.13 E negative 4. All right, and then distribute to the X, and it will be minus that value X.
Wait, how did you?
What's your question?
Yeah, how did you get 3 point?
I distributed 4.4 E negative 4 times 0.712. All right?
Wait. Where'd you get, wait, why is it minus 4.4?
So this is to a negative exponent minus another expression to a negative exponent. Now, remember, for our calculator to like us, this must be a 0 equals equation. Therefore, to move everything around, it would be 0 equals x squared plus 4.4 e negative 4x minus 3.13 e negative 4.
Did you just like really calculate myself first? Or is that like
So we'll want to use the solver on your graphing calculator.
Cummings, I think you're going a little fast for us.
Me?
Yeah, they're
for yours? It's like
okay, Mr. Cummings, look at this.
Right. So
I
the
put
E1
this.
is 0. The E1 is 0. Because look, in our equation, E1 equals, we want 0 equals. Now type in the other
Well,
half.
it doesn't matter which way it goes. I don't know. Then we just put this, and we always keep that zero.
For this unit. Anybody else want me to look at their solver for this red equation that we're on?
And we put alpha.
No. See that green solve?
how do you do your test? Oh, okay.
Okay, good. Glad you know this.
Wait, Cummings, is it? Do we have to put alpha?
Wait, did you click solve afterwards?
What?
Do I have to put zero in equation two?
No, you're missing the x. There's an x
Oh.
on that middle equation. Yes, yeah, put 2 for your guess, and then green solve.
Oh,
You needed to solve.
Yeah.
There it is. There she is. There she is! Looking through the window. I get an x to 2 sig figs
Crap.
of 0.17. No, it's not 2 sig figs. Oh, no, it's 3 sig figs. Sorry. It's 3 sig figs. Of 0.0175.
What I do? No, don't. Oh, I see it. No, I don't actually.
Wait, is it 0 point? Wait, what?
I did. Already matched.
Wait, how did you get 5?
Because my calculator says 0.01747.
Mine says 0.
Yeah, okay, so
179.
Looking at that, when we put in the
I got
equation where we,
0, 0,
equal it
1,
to
9.
x squared, it came out to 7.3, but when you put in like with the fraction equals another fraction, it came out to 8.
What I mean, are you putting? This is how I want it to look exactly. The red writing I have.
Okay, but like the blue one above it,
Yeah.
I put that into the calculator and it came out to 0.017473.
But
But then when you put it the fraction in the blue writing,
what fraction?
the bottom of the board. That
Okay.
one, that fraction,
Yeah.
that
Oh,
came
why'd
out.
you?
That came out to 0.017481.
But it's not the same.
It's not.
Yeah, you know, on the side note, you type more than zero.
I mean, this one right here in red is what should be finding x. Nothing
Why are
else.
they different?
Because the 3.13 is positive on the top one.
Yeah, I've got signs reversed here. This is adding to the x expression. This is subtracting the x expression. I mean, but it should. But your solver is set up for a 0 equals Like, there's probably a better answer to what you're asking than I know, but I don't know why the calculator does it in 2 different ways. What I do know is to get the chemically correct answer, you need a 0 equals expression for a quadratic. I'm sorry, it's not a better answer. Hey, but here's where I really need you to be careful because we are not done. You've got to realize what X is. X is simply the concentration of the OH minus. What are we looking for? We're looking for pH. Like, we're still multiple steps away, y'all. Because in order for us to find pH, I would need an H plus concentration. Now, to find that, I know that I can go 1E negative 14 and divide it by an OH concentration. And that will give me an H plus concentration, which is good to get me towards pH. But again, it still won't actually be done. So 1E negative 14 divided by 0.0175, I get a value here of 5.71. E negative 13 molar. And this is H plus. And then once we have that, now we have the strong type of species. Now finally we're back to the F5. Negative log of a strong concentration will give you pH.
How many questions of these are you going to put on the test?
17.
Oh.
Just kidding. I don't know. I don't remember what the test is. But once you get in a rhythm, I mean, I'm teaching this, and I'm taking a million breaths between steps. Once you're in a rhythm, you're good. So negative log 5.7, E negative 13. Hooray, y'all. We have a pH of 13.244. Is that what you got? Oh, no. My bad. I typed in negative 14. Bum, bum, bum. Okay, let's go again. How about 12.244? Well, we have 3 sig figs, so we gotta go 3 numbers past the decimal.
Yeah, I got 243.
0.243?
That's
I wonder what I typed in. Oh, I didn't put the 1 in there. So pH, therefore, equals 12.243.
See, you can put one of these problems in sets and just gonna leave it blank.
Y'all have a good day.
I understand this lesson.